All right, hello again, everybody. I got another video this time for 9.2. Sit in the same office. Hopefully this time I won't be interrupted too much. All right, so if you think back to yesterday, 9.1, we got a chance to see how to take derivatives and second derivatives of parametric curves using two different formulas. You'll see them at the top of your page there for 9.2. Taking the first derivative, dy dx, and the second derivative as well. As with our two-variable curves that we've seen earlier this year, though, we can also find the arc length of a parametric curve. In fact, we can actually use the formula we've already learned for the arc length of a curve and kind of reshape it to fit our parametric curves. So let's do that first. All right, so if you remember, our formula for the arc length of a curve, not in parametric form, but in sort of our normal two-variable form, looked like this, right? That the arc length was the integral from a to b of the square root of 1 plus dy dx squared dx is what we used, or we said dx dy squared to dy. But we'll use this for now just to kind of explore how to get the equation for the arc length of a parametric curve. So let's do a little bit of a math trick. Remember, as long as we can re-express things as 1, it's equivalent. So let's say that this is going to be equal to the integral from a to b of the square root of 1 plus, and it'll look a little funny, but let's do it. Let's call this right now, since we have dy dx, let's rewrite this in an equivalent form based off of the formula we know from yesterday, that dy dx is really equal to dy dt divided by dx dt, because that's equivalent, right? They are equal to each other. Okay, there we go, dx on the outside still. All right, so we haven't done anything too fancy. We just broke down dy dx into the formula that we knew from yesterday. Okay. From here, though, we could also say, well, wait a minute. Dx, we don't really like dx's in parametric curves. We want some dt's and stuff in here. So let's actually rewrite this. Well, dx, if we want to, we could say, well, let's call this dx dt and multiply it by a dt. That would be equivalent, right? We're essentially, multiplying by 1 here. This is an equivalent form of dx. All right, so that's not too bad. Let's rewrite this and break it down again. We can call this the integral from a to b of the square root of 1 plus, this fraction is going to get kind of big here, but let's call it dy dt squared over the quantity dx dt squared. And we will leave on the outside here still our dx dt dt. All right, cool. Now we can be a little clever here. We can, if we think about this, if we want to, we can factor out. We have a dx dt squared here, right? A dx dt squared. If we went ahead and factored out of the inside here, I'm going to squeeze into the bottom down here. You go from a to b of the square root of. If I factor out of both the 1 and this thing, a 1 over dx dt squared. If we think about that, if I'm factoring it out of 1, that means I'm going to have a dx dt squared that appears in place of that 1. Because if I multiply this back in, dx dt squared divided by dx dt squared will give me 1. Plus, if I factor dx dt, 1 over dx dt squared out of that, factoring 1 over dx dt squared out of that, then we would be left with dy dt squared. There we go. And on the outside here, we would still have, for now, dx dt dt. We're just kind of being fancy and clever with how we're rearranging some things and factoring some stuff out. Now we could take that. I see over here we have the square root of 1 over something squared. So I can take the square root of that and move it to the outside. That would leave me with 1 over dx dt. But because it's inside a square root, we're taking the square root, it's going to be positive. So we'll write it like this. We'll write this as equal to our integral from a to b of 1 over dx dt but absolute value of that, because if we're taking the square root of that thing in front, then it'll end up being positive naturally. And so we'll have that times the square root of the quantity dx dt squared, which is still on the inside, plus dy dt quantity squared, which is still on the inside, as well as our dx dt dt, dx dt dt, and with a little bit of cleaning up, you go, oh, wait a minute, this is going to be 1 over dx dt, and this is going to be dx dt. And if we assume that we're tracing out this curve from like left to right, we can drop these absolute values and essentially cancel out those two derivatives, leaving us with the integral from a to b of, we basically lose that and that from each other, 1 over dx dt and dx dt, leaving us with the integral from a to b of the quantity dx dt squared plus quantity dy dt squared and dt. All right. There we go. That will give us the arc length of a parametric curve from A to B, as long as, so A and B are t values, A and B are t values, as long as, and here we're assuming that we're tracing out the curve once just along its path. So we're imagining a curve that goes like that, and we're only tracing it once along its path. If we end up with a curve that doubles back, like then comes back this direction maybe, we would have to figure out where it turns around and comes back and calculate those things separately. So this formula does assume that we're moving continuously along a path in one direction. We don't double back. All right. Sometimes you'll even see, to make things more clear in writing, this whole integrand part, sometimes you'll see people call it ds, that ds is equal to that thing, dx dt squared, square root of dx dt squared plus dy dt squared. Sometimes you'll see people call that whole thing ds, and they'll simply say the integral from a to b of ds. If you want to work that way, you can, to make things easier to write out. I typically don't. So that's where our arc length formula comes from. This one right here is kind of our big one for the day. It's what you'll need to know. Obviously, it will involve some derivatives, so we'll need our derivative rules. A lot of the integrals do become complicated, so we'll either use ways to simplify it, or our calculator to actually evaluate that integral. All right. So let's look at some examples. That's our main formula for today. Let's go down to example 1, and let's investigate how to use this, okay? My whiteboards are getting a little stickier and stickier each time I do this. I think it's about time for me to buy new ones. The coating is starting to come off. Okay. Okay. So let's look at example 1, which says we want to find the arc length of the curve defined by the parametric equations 3 sine of 3t. So there's our x. 3 sine of 3t. And our y is defined as 3 cosine of 3t. And we want it on the interval 0 less than or equal to t less than or equal to 2 pi over 3. And the reason I'm going to choose 2 pi over 3 is if you think about these two curves, what is the period of sine and cosine? Well, it's going to be what takes the inside around a whole 2 pi. And if we go from 0, that'd be sine of 0, to 2 pi over 3, 3 times 2 pi over 3 will give us 2 pi. This is a whole period of both of these things. So that's why I've chosen this. That means it will only go through this curve once, so we can use this formula. All right. So let's find our arc length. To do that, as we saw over here, that means we need the derivative of x with respect to t and the derivative of y with respect to t. So we'll go ahead and do that. The derivative of x with respect to t is going to be, I'll keep the coefficient 3. The derivative of sine is cosine, but we always got to be on the lookout for a chain rule and all our derivative rules. It's the cosine of 3t, but then times the derivative of the inside, so that's times another 3, That means our dx dt is really 9 cosine of 3t. We'll also take the derivative of y with respect to t, so dy dt is going to be 3. Oh, but we take the derivative of cosine, so it's going to be negative 3 sine of keep the inside, but the inside has its own derivative. That's not 1. So it's a chain rule, just like over here. Chain rule, multiply there. So our derivative is negative 9 sine of 3t. Great. We have our dx dt and our dy dt. We have all the things we need. That equal sign is starting to blend in there. Oh no. Equals negative 9. Okay. So let's go ahead and put those derivatives into our formula here. We can do that. So that means our arc length is equal to the integral from 0 to 2 pi over 3 of the square root of, we take our dx dt and we square it. So that'd be 81 cosine squared of 3t plus, then we'll take our derivative over here and we'll square it. 81 sine squared of 3t. And then in our formula, so we took the derivative of x squared plus derivative of y squared, and then we need our dt over there. All right, we can clean this up a little bit. This integral looks a little painful to do. Fortunately, we got some cosine squared, sine squared in there, so that should be nice. Let's think about it this way. We have an 81 and 81. We could factor both of those out. What's the square root of 81? Square root of 81 is 9. So this is going to be 0 to 2 pi over 3. Factoring out the 81 out of that and then taking the square root of that, it gives us 9 square root of cosine squared of 3t plus sine squared of 3t dt. Well, wait a minute, we have a sine squared plus a cosine squared of some angle. We know that identity is our Pythagorean identity, so that's really just 1. This gives us then the integral from 0 to 2 pi over 3, square root of 1, which gives us 9 dt. All of a sudden, our integral actually becomes very quick to do. The antiderivative of 9 is 9t, evaluate at 0, 2 pi over 3. So when I plug in 2 pi over 3 and multiply 9 times 2 pi over 3, that gives me 18 pi over 3. Minus I plug in 0, 0. 18 pi divided by 3 gives us 6 pi. All right, you may go 6 pi. That seems like a nice kind of thing. That sounds like a circle thing. Well, that's because it is. These two things up here are really just circles with a radius of 3. And when you think about, wait a minute, circle with a radius of 3, we just found the arc length. That'd be a circumference of a circle. If this is a circle with a radius of 3, the formula for circumference is 2 pi r. 2 pi times 3 gives us 6 pi. Hooray, there we go. So there's our arc length. We had to find the derivatives of d of x with respect to t and y with respect to t and use our formula to evaluate the arc length. There's example 1. Let's take a look now at example 2. Another find the arc length thing, okay? Hope you're having a good day. Get ready for February break. I'm sorry I can't be there again today. Enjoy your time off. All right, let's look at example 2. We're going to use, obviously, our same formula over here for arc length, okay? Formula for arc length. This time, we're going to look at a parametric curve that's defined a little differently. Notice it's a little more complex. We might have to do a little more thinking. But we have a parametric curve that's defined by the following equations. We have x is equal to cosine cubed of t, and y equals sine cubed of t. 0 is less than or equal to t is less than or equal to 2 pi. Let's go ahead and do this one then. Like last time, we need our derivatives. Looks like we will have a chain rule again. We have cosine of cosine cubed. So the cubed is our outside element here. We always got to remember that for these trig things squared or cubed. So we'll bring down the 3, keep the inside element, which is cosine, but now it's squared because we used our power rule, times the derivative of the inside, which was cosine. The derivative of cosine is negative sine of t. We can clean that up and call this, let's call it negative 3 cosine squared of t sine of t. All right, then we need the derivative of y with respect to t, so dy dt is equal to, I'm going to have another chain rule here because we have sine cubed. So I'll bring down the cubed, keep our sine, this time it'll be squared of t, and then times the derivative of sine, which is cosine of t, and there we go. We have our 2 derivatives that we will need to be able to put it into our integral formula. So let's go ahead and do that. We have to square those when we get them in there, though. So our arc length is going to be equal to the integral from 0 to 2 pi of the square root of, this is going to be a little bigger this time, dx dt squared. So that's going to be 9 cosine to the 4th of t sine squared of t, right? And we're going to add to it plus, if we do dy dx squared, that gives us 9 sine to the 4th of t cosine squared of t after we square it all, and then dt. So we got to be a little clever here. We can figure out our inside parts. Okay, it looks like if we do some factoring here, 9, we have cosine, we have at least a cosine squared that's shared and at least a sine squared that's shared. So we could rewrite this maybe as 0 to 2 pi. Let's factor out a 9 cosine squared and a sine squared. So that'd be the square root of 9 cosine squared of t sine squared of t times the quantity. Well, what's left over then? If I take out a 9 cosine squared and a sine squared, what's left over in this first part is just a cosine squared of t. You can check by distributing to get back to that. Plus, if I factor out a 9 cosine squared sine squared from all this, I'd have a sine squared left over. We like having cosine squareds plus sine squareds together. That makes simplifying easy because this just boils down to a 1, right? Cosine squared plus sine squared, that's just 1. So then I get the integral from 0 to 2 pi of the square root of that whole thing is 1, so I'm going to forget about it. And I'm going to call this 9 cosine squared of t sine squared of t dt. Wait a minute, all of these things are squared, right? All of these things are squared. Okay, all those things are squared. So what does this mean? This means that the square root of those things squared is going to be equal to the integral from 0 to 2 pi. We're going to use the absolute value because this thing will stay positive. It'll be the absolute value of 3 cosine of t sine of t, right? dt. So we're very close now. We got an absolute value in there, which is kind of not great, but we can think for a second. Well, wait a minute. Cosine and sine, I want this whole thing to be positive. Cosine and sine are both positive as long as it be from 0 to 2 pi. 0 to 2 pi, that's a fourth of our unit circle. So what if I do a quick change on this to make this integral just from 0 to 2 pi? That'd be a quarter circle, and then just multiply my answer by 4. So I'll do that. It looks like here then, I can rewrite my integral as the integral from 0 to pi over 2. Oh, that's not going to look at pi. Is it pi over 2? So that's a fourth of this, but that's because that'll make cosine and sine from between 0 and pi over 2. Everything in here is going to be positive anyway, so I'll lose the absolute value sign. So this is going to be 3 cosine of t times sine of t, and that's okay to do as long as I remember to multiply my final answer here by 4, because I'm taking a quarter circle basically, quarter of the route, and then multiply it by 4 to get the full 0 to to 2 pi. Okay? Right. So that's dt. We got to think for a second about, okay, our integral there. If you want to, you can do a u substitution. We could choose our u to be sine. If u is sine, we can change all of our stuff. If u is sine of t, that means du dt is cosine of t, which means 1 over cosine of t. du equals dt. We come up here, it would cancel out the 3 sine of, cancel out the cosine, and we get something like this. Then this would be the integral of, we got our change our endpoints here. Change our endpoints. So if t was pi over 2, that means our u, this is a good review of u substitution. Then our u is, let's see, the sine of pi over 2 is 1. If our t was 0, that means our u was sine of 0 is 0. And we are pretty close. So this would be the integral from 0 to 1 of 3 sine is u. dt is cosine of 1 over cosine of t du. So that's going to be cosine of tu. dt is 1 over cosine of t du. This is going to be 4 integral 0 to 1. Our cosines will cancel out, and we have 3u du. If you don't want to do all that u substitution, you can handle most of that in your head probably, if you would like. And then we take the integral of that. The antiderivative of 3u is going to give us 4 times 3u squared divided by 2. Evaluate from 0 to 1. We can go ahead and plug in there 1, and that'll give us, what would that be, 1 times, my brain is all over the place this morning. That'd be 3 halves, that's 4 times 3 halves, which would give us 6 in the end. So our answer here then is 6. Our arc length is 6. Slightly more complex example because we had to do some manipulation of our inside of our integral there, then use what we know about trig to realize we need a quarter circle. Then we multiplied our quarter circle by 4, did a u substitution, and got 6. So those are the 2 examples I wanted you to see. The rest of the practice problems are there below with my answers online. For the practice problems, I just want you, it's not in calculus, just to write out the integral that would find the arc length. You don't have to actually evaluate the arc length. Don't forget, after you've done the practice problems, to check your answers. Then try the concepts online. By the end of class, take the comprehension quiz. The break homework, there's a packet, February break homework packet, as well as some homework from the textbook. Please read carefully about whether things are calculated or non-calculated. Have a great rest of the day. Bye.